All right, so we finished section 1.5, and in that we were talking about matrices and a specialized type of a matrix called a Boolean matrix. We're going to jump ahead into chapter 4.2, and we're going to talk about a brand new discrete structure that is related to a matrix, and it's called a relation. So a relation can be defined as a set of ordered pairs made up of related elements. Now, we have talked about ordered pairs before. This is not a new topic. The fact that it is an ordered pair means that the first element is generating the second element, that the first element is related to the second element. We've talked about sets before. And so now we're going to expand that concept into this thing called a relation. So a relation is a set of ordered pairs that are based upon the product of one or more set, the cross product of one or more set. So let's say, for instance, that we have set A and that we have set B. If we were to do the cross product of A cross B, it is going to give us a number of ordered pairs or related elements. This cross product is going to give us all possible elements. So let's say, for instance, that A is the set that contains, let's say that it has 5 elements, and let's say B has 3 elements. When I do the cross product of A and B, this is going to give me 15 possible elements that we can cross. And so if A cross B is the set of all elements AB such that A is an element in A and B is an element in B. A relation is going to be the subset of all of those elements, the subset of A cross B. The way that we can define each one of the individual elements or each one of the elements in the relation, we can say that A is related to element B. Another way is to say that the ordered pair AB is an element in the relation. If A is not related to B, we would say that the ordered pair AB is not an element in R. This should be notation that we are familiar with because we have done sets before and we have listed out subsets before as well. So this should be familiar to us. So we can say that if this ordered pair AB is an element in R, then A is related to B by this relation that we are going to call R. They are in relation to one another. So let's talk about the cross product. We're going to find out that A cross B, this means the cross product. The cross product, let's say that A is the set of urns and it contains, I can't remember out of the homework assignment, I'm pretty sure one of them was gold and one of them was copper. We had another set, we'll call it B. I'm pretty sure that this was the colors. And I'm going to say red, green, and blue. I can't quite remember what those colors in our homework assignment was. The cross product means that I'm going to take each of the elements in A and I am going to multiply it by or connect it to each of the elements in B. So for instance, for each one of the elements in the urns, I'm going to start with gold, and for gold, then I'm going to cross it with or connect it to each one of the colors. So we're going to say that we have gold and red. We also have gold and green. And then we're going to have gold and blue. We'll do the same thing with the other element in A. The other element was copper. So copper is also going to be connected to red. Copper will also be connected to green. And then finally we will say copper and blue. Now, as I mentioned before, as I said before, that if there are 5 elements in A and there are 3 elements in B, there would be 15 elements total. So let's see if this worked. A had 2 urns and B has 3 colors. If I do the cross product of urns and colors, then I'm going to have 2 times 3, which is 6. So the question is, do I have 6 elements in here? I absolutely do. There are 6 different unique combinations of urns and colors. And so we're going to find out that a relation is actually a subset of those options. It is a subset of the cross product of one or more set. So for this instance that we had here, we had 6 elements in the cross product of urns and colors. So I might define a relation as, and remember, a relation is a set. So let's just pick a couple of these. How about if I say gold and red? That would be one of the ordered pairs, one of the elements of my relation. Let's do another one. We'll say copper and green. That would be another one. And then how about if we say gold and blue? And I'll pick a 4th one, copper and red. How about copper and red? So that begs the question, is this a subset of the cross product of all of these elements? If this is the cross product of the urns and the colors, is this relation a subset of that cross product? And it is just one of the subsets. A relation contains 0 elements of the original cross product, or it can contain all of the elements of the cross product. This one contains 4 of the 6. So the next thing that we're going to see is that we can also do the cross product of a set with itself. We can have the cross product of 2 separate sets, or we can have the cross product of a set with itself. So let's say, for instance, that I have set A. Let's say, for instance, set A contains 1, 2, 3, 4, and 5. There are 5 elements in set A. So if I wanted to do the cross product of A with itself, I'm pretty sure that A has 5 elements in it. This is going to be 5 times 5, which means that there would be 25 possible ways that I could cross A with itself. And if a relation is just a subset of that, let me define a relation. Let's say that we have a relation that contains the ordered pair 1, 2, 1, 4, 2, 3, 3, 5, 4, 3, 5, 4, and 5, 5. Let me make sure that I got all of those right. 1, 2, 1, 4, 2, 3, 3, 5, 4, 3, 5, 4, and 5, 5. Of course, these are ordered pairs, and so there would be commas between each one of the individual elements. So, if somebody were to say, what about the ordered pair 2, 6? Well, 2, 6 is not a valid ordered pair because 6 is not even an element in the original set A. So if we can have, this is indeed, if I were to cross all elements of A with itself, there would be 25 different combinations when order matters. Because 1, 2 is a different ordered pair than 2, 1. So there would be 25 different elements. I have selected 2, 4, 6, 7 of those 25. I do indeed have a subset of A crossed with itself. So we're going to find out that there are some properties that we can define on a relation. So the first one is the domain. The domain of a relation is the set of all first elements in the ordered pairs. the set of all first elements. So if I look at this particular relation, I can say that the domain of this relation, I'll call it the domain of this relation, is the set of all ordered pairs. It is a set. Notice it uses the word set, so I'm going to have to use set notation. And I'm going to look for all the first elements. I see a 1, I see a 1, a 2, a 3, a 4, a 5, and a 5. This begs the question, is that a valid set? Well, we learned from our set notation that we cannot have repeating elements. And so I'm going to have 1, 2, 3, 4, and 5. No repeating elements. I know that 1 is used a couple of times. That's acceptable. I'm just going to ignore repeating elements. So if a relation R can have a domain, it can also have a range. And what do you think the range is? If the domain is the set of all first elements in an ordered pair, what do you think the range is? Yeah, you're right. It's the set of all second elements in the ordered pairs. All right, so it would be considered, we could call it the range of R. Let's see if we can find the range of this particular relation that we're looking at right here. If it's the set of all second elements, remember it is a set. I see a 2 and a 4 and a 3 and a 5. I also see a 3, a 4, and a 5. But what do we know about duplicate elements? The 3, the 4, and the 5 are already are already present in the range, which means all I really need is the 2, 4, 3, and 5. As I'm listing elements in a set, the order of the elements themselves don't matter. So if I felt the need to make sure that these were sequential in nature, I could change it to 2, 3, 4, and 5. But this is an acceptable representation of those. So I said the relation is a subset of all possible combinations of a set, either crossed with itself or with another set. But sometimes it might be too difficult for me to list out all of the elements in the range. I see that this range that we were just looking at had, how many different elements did that have? 2, 4, 6, 7. 7 different elements in the range. So another option, instead of listing out each one of the individual ordered pairs within a range, another one of the options you might find sometimes is to give a function that actually would define those. So let's say, for instance, that I had set A that contained 1, 2, and 3. And I had set B that contained the integers 1 through 7. And I am going to define the range as, instead of a set of ordered pairs, I'm going to define it as the set of all A, B such that A is an element in A and B is equal to 2A plus 1 or 2A plus 1 or B is equal to 2A minus 1. So now I have a function, and from that function I should be able to generate the elements of the set. So let's see if we can do it. A is an element in A, which means that I am going to start with each one of the elements in A. So this relation is going to be the set of all elements. I'm going to start with 1. 1 is the first of the elements in A, and this says that B can either be 2A plus 1 or it can be 2A minus 1. So if A is 1, then 2A plus 1 is 3. So one of the elements is going to be a 1 and a 3, but there is also an OR, so another one of the options for the second value of B is 2A minus 1. Well, if A is still 1, then that is going to be 2 minus 1, and that's 1. So now I have a 1 and a 2, All right, so it says A is an element in A, which means we have done the first value of A. Now we need to pick up the second value of A. And so if A is 2, 2A plus 1, that would be 4 plus 1 is 5. But another option for 2 is 2A minus 1. That would be 4 minus 1 is 3. All right, so then I've done the 2. Now I need to do the last set, which is 3. So if A is 3, 2A plus 1 is 7. 2A minus 1 is 6 minus 1 is 5. So using a function, I can now define each one of the individual elements of the relation. And because I have a relation on my hands now, I can actually find a domain and a range. So what is the domain of this relation R? Remember, the domain is a set, and the domain is all first values in the ordered pairs. And I see 1, 2, and 3 are all the first values. I see that each one of those are repeated, but we're going to ignore those repeated values. And then we're going to find the range of R. Remember, the range of R is the set of all second values. Without repeating elements, I see a 3 and a 1 and a 5. That 3 is repeated. I need to pick up the 7, and that 5 is also repeated. So I should have 3, 1, 5, 7. The order in which the elements appear doesn't matter, so I could rewrite it to 1, 3, 5, and 7 if that made me feel a little bit better about it. All right, does anybody have any questions, comments, thoughts? All right, it's your turn. So the confidence that we have talked about, the elements in your confidence for 4.2 would be, we talked about a relation, we talked about the domain and the range of the relation. Those are in your confidence for 4.2. So the next thing that we want to do is we want to explore different ways that we can represent. What are some different ways that we can represent this relation? Ultimately, we're going to concern ourselves with 3 different representations of the relation. The first one that we have been talking about is the set of ordered pairs. The second type of representation of a relation that we want to talk about is a matrix. And what we're going to do with a matrix is we're going to say that the matrix of a relation is actually going to be mapping each one of the individual elements in a relation to a matrix. So we're going to map the ordered pairs to a matrix, which I should never use the definition of the word in it. I should never use the word in the definition of the word, so maybe we should talk about what a matrix is. We were discussing Boolean matrices earlier. And so the matrix, or a Boolean matrix, is made up of 1s and 0s. So what we're going to do is map the ordered pairs to a Boolean matrix in much the same way that we were mapping the min terms in a truth table to the Carnot map. So we were creating these truth tables with x, y, and z values, and we were finding all of the individual min terms in the truth table. And then we created this Carnot map that looks like a table or it looks like an Excel spreadsheet. And whenever I found a min term, I would map it to the Carnot map, finding its position. If the min term existed, I would put a 1 in its position. And ultimately, if the min term didn't exist, we were kind of leaving it blank. For the purposes of my matrix, I am not going to leave it blank. I am going to map either 1s or 0s. So we're going to have either 1s or we're going to have 0s on our Boolean matrices. So the first thing that I need to do if I'm going to map a relation to a Boolean matrix is I probably have to decide how large the matrix needs to be. So let's say, for instance, that I have a cross product of A. I have a relation that is defined over the cross product of A with itself. And if A is a 3, or excuse me, if A has 3 elements, then that means when I do the cross product, I'm going to have 6 total elements. So the matrix that I am going to create, the Boolean matrix, is going to contain it needs to contain 6 elements. And so I'm going to map the rows to the first set that we use the cross product, which if I am just doing A crossed with itself, that means that the rows are going to be 1, 2, and 3. The columns in my Boolean matrix are going to be the elements in the second matrix. Since I am just crossing A with itself, ultimately there are going to be 1, 2, and 3 columns, which means that I should have 6 total columns. If I've done this before, especially when we were multiplying matrices together, but this would be row 1, column 1, row 1, column 2, and 1, 3. This is 2, 1, 2, 2, and 2, 3. This is 3, 1, 3, 2, and 3, 3. And there my math, this is 9. 3 times 3 is 9, not 6. I should have 9 positions or 9 cells in my matrix. If I did A crossed with itself, I'm going to have 9 of those elements. Now obviously if I was crossing a matrix with another one, let's do urns and colors for just a minute, because I'm pretty sure that before we had urns and the cross product of colors. If I remember right, there were 2 urns and there were 3 colors. So if I was going to create a matrix of the relation that is a subset of urns crossed with colors, the matrix is going to have as the rows is the elements of the first one. So I'm pretty sure that we had gold and we had copper. The columns on my Boolean matrix are going to be made up of the elements of the second set, and our second set had colors. I think that we had red. Let me come back up here and look what my colors were. We had red, green, and blue. There it is, red, green, and blue. So I'm going to say red, green, and blue. So 2 times 3 should give me this time, if my math is right, is 6, which means in theory this would be gold red, gold green, and gold blue. This would be copper red, copper green, and copper blue. So I have 6 cells in this matrix when I'm doing the cross product of urns and colors. But the whole point of this exercise was that the matrix of a relation is when I am mapping elements in the relation or ordered pairs in the relation to the matrix. So it's important that I know where each one of the individual cells are. So I'm going to go up there and I'm going to grab that relation that we have for urns and colors, and I'm going to drag it down here and see if we can map it to that Boolean matrix. There it is right there. I'm going to grab this relation right here. I'm going to copy it down below. We're going to see if we can map it right here. Let's map it. So for each one of the individual ordered pairs, I need to map it to its correct position on the Boolean matrix. If the ordered pair exists, I'm going to put a 1 there. So let's see, this is red and gold. So I'm looking for red and gold. That means that red and gold exists. I'm looking for copper and green. I believe that is copper and green, so I'm going to put a 1 there. This is gold and blue. I believe that is the position for gold and blue. And then finally we have copper and red. This looks like the position for copper and red. I am going to put zeros in the rest of the places, just because it will, as placeholders, it just makes it a whole lot easier to make sure that I have all of my horizontal lines working correctly. Now, one of the ways that I can check my work to make sure that I am on target, 4 elements in my relation, and so I have 4 ordered pairs. So I should have 4 1s in the matrix of that relation. There should be 4 1s. I'm not guaranteeing that they're in the right place, but the fact that I have 4 of them means that I'm most definitely on the right track. And so I actually can define this as the matrix of the relation R. Given the fact that this is the relation R, we now have the matrix of that relation. All right, so I'm pretty sure that we also did a relation on a set A when I crossed the set A with itself. Let's see if we can find the matrix of that relation. There it is. Nope, nope, nope. There it is right there. So now I have this relation for set A. So we're going to see if we can map this relation to a matrix. Given the fact that the set A contains 1, 2, 3, 4, and 5 elements, I'm going to copy and paste this relation. I'll put it down here. We'll see if we can create a matrix for that particular relation over A. I'll even remind myself of the elements of A. 1, 2, 3, 4, and 5. It's important that I understand the elements in A. This relation is defined as A cross A. That is critically important because when I start building the matrix of the relation, I have to know what size it is. So remember I told you that 1, 2, 3, 4, and 5, that the rows are always the number of elements, or not just the number, the elements that are in the first of the two crossed matrix, or excuse me, sets. And then the columns for my matrix are going to be the elements of the second set, which just also happens to be 1, 2, 3, 4, and 5. All right, because I can, this is 1, 1, 1, 2, 1, 3, 1, 4, and 1, 5. This is 2, 1, 2, 2, 2, 3, 2, 4, and 2, 5, 3, 1, It's important that I know what each one of the cells represents so that I can get them in the right place. Because if I don't get them in the right place, it can mess up calculations that I do further. So there are 25 unique elements. There are all 25 combinations when I cross A with itself. But what I want to do is, ultimately, I just want to map the elements in my relation, because this is going to become the matrix of the relation. So I'm going to map the ordered pairs from the relation into the matrix. So let's do it one at a time. This is 1, 2. I'm pretty sure that 1, 2 is going to go here. If it makes my life easier, which it does, I can list the elements of the first set and the elements of the second set across the rows and the columns so that I can try to get my horizontally challenged lines on. The next one is 1, 4. So I'm pretty sure it needs to be in row 1, column 4. The next one is 2, 3. That would be row 2, column 3. The next one is 3, 5. Row 3, column 5. The next one is 4, 3. Row 4, column 3. The next one is 5, 4. That's row 5, column 4, and then 5, 5. So as I said before, unlike a Carnot map where we generally just leave the ones, when I'm talking about matrices, I'm going to have a tendency to fill in the missing zeros. But I'm going to make the ones a different color, kind of so they stand out a little bit. So one of the checks that I can do is I can count. If I have 1, 2, 3, 4, 5, 6, 7 pairs, how many ones should I have on my matrix? There should be 7 ones. If I count them, 1, 2, 3, 4, 5, 6, 7, I see that I have 7 ones there. I make no guarantee that they're in the right place. I should probably double check to make sure that they are all in the right place. But I know at least I have enough of them there. And this is the matrix of that relation. When I map ordered pairs to a Boolean matrix, 1 indicating the pair exists, and 0 indicating that the ordered pair does not exist within that particular relation. All right, does anybody have any questions, comments, thoughts? All right, it's your turn. All right, so let's do it one more time. This time we're going to do it again when I do the cross product of separate matrix. Instead of a single matrix, let's do it as the cross product of two separate matrix. I'm going to change up names. I've been using A a lot, so how about if we say C is a set of elements A, B, C, D, and E. And let's say that D is the set that contains the elements 1, 2, 3, 4, and 5. And let's say that when I do the cross product of C and D, we are going to get the relation from that cross product that is going to contain, let's say it contains B3. Let's say that it has B4, C5, and E1. So that is the relation from the cross product. So how many elements does C have? Looks like it has 5. How many elements does D have? Looks like it also has 5. When I do the cross product of those two, there are 25 possible combinations when I have the two of those together. So if I wanted to create the matrix of this relation, I am going to create a matrix where the rows are the elements of the first, which is A, B, C, D, and E. The columns are going to be labeled as all of the elements from the second set, which will be 1, 2, 3, 4, and 5. And then I am going to map all of the elements in the relation to the Boolean product. So this is A1, 2, 3, 4, A5. This is E1, E5. If I wanted to list them all, this would be B2, E3, nope, not E, C3, D4. So what I want to do is I want to try to map to the correct position the elements or the ordered pairs in my relation. So let's see if we can find, I'll do it again, A, B, C, D, and E. 1, 2, 3, 4, and 5. Let's see if we can find the correct position for B3. Well, this is B, and so I'm going to put a 1 there because that ordered pair exists. The next one is B4, so I'm going to put a 1 in that position. The next one is C5. The next one is, the last one is E1. There should be E1 right there. Now, in order to try to make this as readable as possible, I am going to fill in the zeros. But I didn't make the ones a different color, did I? So they're not standing out so much. If I wanted to do a double check to make sure at least that I have enough of them, there are 4 pairs. As a result, there should be 4 1s in my matrix, my Boolean matrix. Does anybody have any questions about that so far? Where does the relation come from? This relation, we already saw that one of the relations was coming from a function that we had generated, and using the input value of A, it was generating 2 separate output values of B. Now I know that that doesn't define a valid function because we know the definition of a function. A valid function means that one single input cannot generate 2 entirely separate output. But we were using a function to generate that relation. These other relations are just kind of made up. We're going to find out that they actually can mean something, but for our time being, think about the truth tables that we were generating when we had X, Y, and Z values, and then an output column, and I would just give you what the output column was. Ultimately, we wanted to find out what the function was that was generating that, the Boolean expression, that was generating that function. But at the time, we were just writing down an outcome, an output column, And then later we found the Boolean expression for it. So our purpose is here, we are just writing down a subset of the cross product, and we're defining it as a relation. As you well know, there are a variety of different relations over the cross product. So, does that answer your question? Okay. So I said there was a couple of different representations, right? Let me see if I can find it up here. Oh, that was when we first started discussing matrix. Let me come down here. There it is. I said that a relation is a set of ordered pairs. That another way that we can express a matrix, express a relation, is by using a matrix. I actually want to introduce you to a third way that we can represent a matrix, and it's called a digraph. So a digraph, I'm going to come down here and I'm going to explain, or we're going to discuss what a digraph is. A digraph is another visual representation of a relation. It's another way that we can represent or express a relation. A digraph is short for directed graph. And it is going to be a graph that we can use to map out ordered pairs within a relation. A digraph is made up of nodes, sometimes referred to as vertices or vertexes. It's also made up of arrows, sometimes referred to as edges. So a node represents any member of the set. A node is any member of, I'll call it set A, or for doing the cross product of a set A and B, it would be any member of set A and B, a cross product of, any member of those sets. The arrows are actually going to represent any, they're going to represent an ordered pair. In the relation R. So a digraph, a directed graph, is made up of nodes and arrows. So it might look like if this was node A and this was node B, and they were an ordered pair, I'm going to have an arrow that is moving from A to B. This would represent the ordered pair AB. So the nodes are going to be circles with the name of the element inside of it, and the edges are going to be arrows pointing in the direction of the relationship between the ordered pairs. So let's see if we can create a digraph, or if we can draw a digraph of, well, let's go back to A. Let's go back to this one. Where is it? This one right here. Let's see if we can draw a digraph of this particular relation. I am going to put that relation right there. I'm going to remind myself that this relation is coming from the set A, which is made up of 1, 2, 3, 4, and 5. That the relation is coming from the cross product of A with itself. That is critically important, because if I'm going to draw a digraph of it, I need to know what the individual nodes are. Since it's the cross product of A with itself, and A contains 5 elements, I need a node for each one of the 5 elements. That is going to be 1, 2, 3, 4, and 5. I could lay them out horizontally or vertically, but I'm pretty sure the next thing that I'm going to have to do is to map all of the ordered pairs to edges on my digraph. So the first one says that it is the ordered pair 1, 2, which means that I am going to put a directed arrow. I'm going to put a line, a directed line, between the nodes 1 and 2. The next one says that it is the ordered pair 1, 4, which means that I'm going to put an arrow from 1 to 4. The next one is 2, 3, so I'm going to put an arrow from 1 to 3. The next one is 3, 5, so I'm going to put an arrow from 1 to 5. The next one is 4, 3, so I'll put an arrow from 4 to 3. Then we'll do 5 to 4, and this one right here is 5 to 5. How in the world am I going to get 5 to 5? So it's going to be an arrow that loops back in on itself. So this is the digraph of the relation R. Once again, if I wanted to check myself, I could say that there are 1, 2, 3, 4, 5, 6, 7 pairs. If there are 7 pairs on the ordered or on the relation, there should be 7 arrows on the digraph. Let me count them. There is 1, 2, 3, 4, 5, 6, 7. 7 arrows on the digraph, 7 pairs in the relation. That doesn't mean that I have my arrows between the correct nodes, but it does mean that I have enough of them. I would probably want to double check and make sure that I have them going in the right place. So this is a digraph. It is a visual representation of a relation. So we can have a digraph that is showing the relation when it's a cross product of itself. Can we have a digraph of a relation when it is 2 different pairs, 2 different sets? And here we go. Let's see if we can come back to our urns and our colors. I'm pretty sure that I had a relation that was defined over 2 separate sets, urns and colors. So I'm going to come down here and we're going to see if we can draw a digraph over this pair of sets. Let me put the relation here. I'm going to have to remind myself what the original sets were, mainly because that's the nodes that I'm going to have to write. And so if if the urns was made up of, it looks like gold and copper. It was the set that contained golds and copper, and we had a set called color, which was made up of red, green, and blue. That's what it looks like, red, green, and blue. And then we have a relation that is defined over urns by colors. That means that what I need to do is I need a node for every single element in both of the 2 unique sets. So this one might be kind of simple, but it would seem that I could put gold here, and I'm going to put copper. I might need a bigger thing, copper. So I'm going to put gold and copper here. I'm going to put red, put green, and I'm going to put blue. So there should be 5 elements, because there are 2 here and there are 3 here. If I add them up, I should have 5 total elements. Now I am going to map the ordered pairs from the relation. There it is right here. I'm going to map the ordered pairs to my digraph. So the first one is gold and red. So I'm going to have an arrow going from gold to red. The next one is copper and green, so I'm going to have copper going to green. The next one is gold and blue, so I have an arrow going from gold and blue. The next one is copper and red. So there is a digraph. A digraph when I have a relation that is defined over the cross product between 2 separate sets. So the nice thing about a digraph, it's a visual representation. If I'm just looking at the relation at the top of my screen with the 4 elements, oh, there we go. We should probably double check that just to make sure. I have 4 pairs. I should have 4 arrows. 1, 2, 3, and 4. It looks like I have all 4 of them. I'm not guaranteeing they're in the right place, but I have them. The one thing that a digraph can help me know is which pairs are represented and which ones are not. I can tell that gold is not connected to green just because looking at my digraph, there is no arrow between gold and green. I can visually inspect it and see that copper is not connected with blue. It may not be so easy for me just by looking at the relation to tell that copper and blue are never combined in this particular relation. But looking at the digraph, I can tell it quickly and easily. The same thing can be said of my digraph here. There are 7 pairs. Out of the 25, the relation is made up of a subset of 7 of them. And just looking at the ordered pairs, I may not be able to tell immediately which ones are missing, which ones are not represented. But if I look at the digraph, I can see that there is no arrow from 1 to 3. I can see there is no arrow from 5 to 2, or from 2 to 5 for that matter. So it is a visual representation that quickly allows me to identify, this is the digraph of the relation, quickly allows me to identify the ordered pairs that are represented. So ultimately what we would like to be able to do, just like I wanted you to feel comfortable moving from Boolean expressions to truth tables to digital circuits and back, remember? 3 representations of the same thing. We're going to find that these 3 are all representations of the same thing. That I'm going to have the digraph of a relation, I'm going to have the matrix of a relation, and then I'm going to have the relation, the ordered pairs of the relation, and I should feel comfortable moving between the 3 representations of this relation, either ordered pairs, as a digraph, or as a matrix. So do we have any questions about this? All right, return. All right, so everything that we have done so far is we have started with a set of ordered pairs, and from that set of ordered pairs we have come up with the matrix and the relation. But if I truly want to be able to move through the 3 representations of a relation, I should be able to go backwards as well, or maybe I should say in a different direction as well. So let's say that I have this set 1, 4, and 5. And the digraph of this relation looks like this. Since there are 3 elements, 1, 4, and 5, I'm going to put them in a circular motion because I'm pretty sure that I'm going to have some arrows that are connecting them. So we're going to go 1 to 4, and we're going to go 4 to 1. Then we're also going to go 4 to 4. And we'll go 5 to 4, 5 to 5, 1 to 5. So given this digraph of a relation, can I find the matrix of the relation? I'll say given the given the digraph of the relation, find the matrix of the relation. How am I going to start with a digraph and go to a matrix? Well, perhaps one of the ways that I can do that is by finding the ordered pairs. So let's see if we can define the ordered pairs that make up this particular digraph. So we're going to see if we can find the relation. This might be a really good way for me to take a digraph and to find the matrix of it is to identify each one of the individual ordered pairs in the relation. And remember, the ordered pairs are the edges or the arrows between the sets. So I'm going to mark them off as I write them down. This one is an arrow from 1 to 4. This one is an arrow from 4 back to 1. This one is an arrow from 4 to 4. This one is an arrow from 5 to 4. This one is an arrow from 5 to 5. And this one is an arrow from 1 to 5. Let me make sure that I get that right. So I'm going to double check. This is 1 to 4. This is 4 to 1. This is 4 to 4. This one is 5 to 4, 5 to 5, and 1 to 5. So now, do I have all of the arrows? It looks like I've accounted for all of the arrows. The next question is, I have the right ones, I've double checked it. Alright, so now it might be easier, now that I have the ordered pairs, it might actually be easier now for me to generate the matrix of the relation. Since it is the matrix of the relation crossed with itself, this is going to be 1, 4, and 5, 1, 4, and 5. Now what I need to do is I need to map these 1, 2, 3, 4, 5, 6 ordered pairs to the matrix. So let's start with this one, 1, 4. It is in row 1, column 4, which would be right there. The next one is 4, 1. It is in row 4, right there, column 1. The next one is 4, 4, which is in row 4, column 4. The next one is 5, 4, which is in row 5, column 4. The next one is 5, 5, row 5, column 5. And then 1, 5, row 1, column 5. So I'm going to fill in the zeros so that I have a full Boolean matrix. Once again, if I have, one of the ways that I can check is if I have 6 arrows, I should have 6 pairs, and I should have 6 ones. As always, I'm not verifying or not guaranteeing that they're in the right place. I should probably double check my work just to make sure that they are in the right place. But this is the matrix of the relation that we had from this digraph. So that's how I can go from a digraph to a matrix. It might be a little bit easier for me to go through the set of ordered pairs in order to do that. All right, does anybody have any questions about that? Comments? Thoughts? All right, your turn. Okay, so the last thing that we want to know, there's one additional property, one additional thing that I want to know about a digraph in particular. And it is called the in degree and the out degree of a node. The in degree of a single node, as a matter of fact, the in degree of each node, the in degree of a node is defined as the number of arrows pointing into the node. It's called the in degree. And it is the number of arrows pointing into a node. So let's see if we can come up here and find, oh, I have a digraph. Let's see if we can come up here and find the in degree of each node in this digraph. Now, each and every single node has an in degree. So the in degree of node 1 is the number of arrows that are pointing into node 1. Well, it looks to me like there's only one arrow pointing into node 1, so the in degree of 1 is 1. Then I need to find out what the in degree of node 4 is. I'm going to count the number of arrows coming in, 1, 2, and 3. It looks like there are 3 arrows pointing in, so his in degree is 4. The last node is 5. It looks like he has 1, 2 arrows pointing in. So the in degree of that digraph, or each one of the individual nodes there, we can list them and find them. Let's see if we can find another digraph. Maybe we can find the in degree of another digraph. Oh, here's one. The in degree of each one of the individual nodes. I'm going to have gold. His in degree looks like 0. I have no arrows pointing in. Copper, his in degree is going to be 0. Red, his in degree is 1, 2. Green, his in degree is 1. And the last one is blue. His in degree is also 1. Every single node in a digraph has an in degree. every node. Whether or not they have arrows pointing in, we got one last one. Let's check this one out. Let's see if we can find the end degree of all of these nodes. I'm going to have 1, 2, 3, 4, and 5. We're going to calculate end degrees of each one of these individual nodes. So if I look at node 1, well, he has no arrows pointing in. If I look at 2, he's got 1 arrow pointing in. If I look at 3, looks like he has 2. 4 also has 2. 5 also has 2. I can calculate the end degree of the nodes on any one of the digraphs. So if digraphs have end degrees, they probably also have out degree. What do you think the out degree of a node is? Right. The out degree is the number of arrows pointing out of a node. So let's come back here and let's see if we can find the out degree. I'll do it in a different color. Let's find the out degree of these individual nodes. We still have 1, 4, and 5. What is the out degree of 1? Well, now I see that there are 2 arrows coming out, so I'm going to say the out degree of node 1 is going to be 2. The next one is 4. The out degree, I see something coming out here and here. That means the out degree of node 4 is going to be 2. The last one is 5. 1, 2. I see that there are 2 arrows coming out of 5, so his out degree is 2. All right, let's look at this one, out degree. Every node has an end degree, every node has an out degree. So gold, the out degree of gold is 1, 2. The out degree of copper is also 2. The out degree of red, there, I don't see anything coming out of red. I don't see anything coming out of green, and I don't see anything coming out of blue. So let's do the last one up here. The out degree, we're going to do one node at a time. The out degree of 1 looks like it is 2. The out degree of 2, I see 1. The out degree of 3, if I can get it, I see 1. The out degree of 4, I see 1 coming out. The out degree of 5, well, there's 1, and then I drew over 1 right here, so I'll just put the 2 there. So every single node in a digraph has an end degree and an out degree. But if I'm actually trying to calculate end degrees and out degrees in a computer program somehow, it can be really difficult for me to get a program to visually inspect a digraph. So it would seem like there would have to be another way for me to be able to calculate that. And the way that we can calculate the end degree and out degree of nodes, another way, is using the matrix of the relation. So let me come on over here to the matrix of this relation right here. If in a digraph the end degree of a node is the number of arrows pointing into a node, in a matrix the end degree of a node can be calculated by adding up the columns. So we are going to sum degree of a node. We are going to sum the column to find the end degree of a node. We're going to sum the columns, which means that I'm going to come up here and I'm going to sum the columns. So 0 plus 1 plus 0 is 1. 1 plus 1 is 3. 1 plus 1 is 2. So I can see that the end degree of node, see this is node 1, the header for node 1. The end degree of node 1 is 1. The end degree of node 4 is 3. The end degree of node 5 is 2. Let me check that out. 1, 3, and 2. There it is. 1, 3, and 2. I think that might be the only diagram or the only matrix. We didn't do a matrix for this one. Oh man, I'm pretty sure we had a matrix for this one. Somewhere. There is the matrix for that one. Let's calculate the n degree. That is the same matrix as the digraph below. Let's calculate. If I want to know the n degree, I am going to sum each one of the individual columns. Looks like that one is 0. Looks like this one is 1. This is 2. This is 2 and 2. Did I count those up right? 0, 1, 2, 2, and 2. I'm going to go down to that digraph and see if I get 0, 1, 2, 2, and 2. 0, 1, 2, 2, and 2. Ah, I have 0, 1, 2, 4, and 2. Where did I get the 4 on node 4? 1, 2, 3, 4. There it is. It's not a 4. I must be dyslexic because when I said node 4, and I wrote down 4, this was 2. If I go back and I check myself, I can see that the n degree for node 4 is 4. All I have to do is count the 2 arrows coming in. So then I double check 0, 1, 2, 2, and 2. All right, let's see if I can do the same thing for the out degree. If the n degree of a node, you sum the columns, how do you think I calculate the out degree of a node? Yep, we're going to sum the rows. So let's see if we can find the out degree of a node using a matrix. There's a matrix right here. I'm going to sum the columns. This time I'm going to sum the 3 columns. So as I sum across, this becomes 2. As I sum across, this is also 2. Oh, no, that looks like 12. I can't have it looking like 12. So I'm going to put, oh, we got to make it look like 12. All right, so this is 2. This is 2. This is also 2. And I have header rows, so I have a header. So node 1 has an out degree of 2. Node 4 has an out degree of 2. Node 5 has an out degree of 2. Let's double check what I found here. There it is, out degree of 2, 2, and 2. I should definitely come up here and check this other matrix because see if, oh, that's not it. We'll come up here and double check this matrix, see if I got it right. So here we go. We are going to sum the columns. Excuse me, we're going to sum the rows to calculate the out degree. We're going to sum the rows. That sums to 1. This sums to 1. This sums to 1. This sums to 2. So we had 2, 1, 1, 2, 1, 1, 1, 2. Let's see if I got that one right. There it is, 2, 1, 1, 2. Very nice. I got all of these right. 2, 1, 1, 1, 2. So I can calculate the n degree and the out degree from a matrix, and I can calculate the n degree and the out degree from a digraph. Each individual node on the matrix and the digraph has a separate and distinct n degree and out degree. The reason why it works when I calculate it from a matrix, I'm going to look at this one really fast and see why. I can sum the columns. If this is the n degree, the nature of, let's see this one right here. I'm going to pick this one right here, and I'm going to see that this corresponds to the ordered pair 4, 1. The ordered pair 4, 1. That means for this header that 4, 1 means that there is something going into 1. So let's try this one right here. This corresponds to 1, 4. This corresponds to 1, 4, 4, 4. And this one corresponds to 5, 4. If you'll notice, 4 is the second element, which means that each one of them is corresponding to something that is going into 4, hence the reason why it is the end degree. So, if I want to sum the end degree, I sum the columns and then I look at the column headers to determine which node it is. If I want to sum the out degree, I'm going to sum the rows because the out degree, this one indicates this is column 5, 5. The very fact that 5 is going somewhere, this says 5, 4, so 5 is going somewhere. This means that 5 is going somewhere. That is the definition of the out degree, that 5 is pointing out or going somewhere. So if I sum the rows and I look at the row header, I'm going to get the out degree of each one of the individual nodes. All right, do we have any final questions about that? What we have talked about in section 4.2 has been relations, which is just a set of ordered pairs. We've talked about the domain and the range of a relation. I should say the relation is a subset of the cross product of a matrix with, a set with itself, or the cross product of a set with another set. And a relation is a subset of those possible combinations. A relation can have a domain and a range. The domain is the first element in the set of ordered pairs. The range is the second element. We also found out that we can draw up the matrix of a relation, which just means that I map each one of the ordered pairs to its position in a matrix, in a Boolean matrix. And then we can have a digraph of a relation, which is just a visual representation using nodes and edges to indicate the ordered pairs. And we found out that each one of the nodes has an in degree and an out degree. I can find those in degree and out degrees using either the digraph or using the matrix. All right, any final questions, comments, thoughts?